All right, so we can talk about the, like I was just saying, the truncation error. And so that's the error that we get, or the remainder that we get when we truncate our series down to a polynomial, right? So if we take our Taylor series and, or it doesn't have to be a Taylor series, but it could be any series for that matter, and turn it into a polynomial. And so if we have a nice, simple geometric series, like this one here, 1 plus x squared plus x to the 4th plus x to the 6th, right, and so on, that we're using to approximate 1 over 1 minus x squared, just a regular old power series, right? Everybody's good with that, that's just a regular old power series, right? True? Yeah, okay, good, right? That's just a regular old power series. We can see pretty easily what the error would be. So I'm going to write out the polynomial that we're going to use. So we've taken 1 plus x squared plus x to the 4th plus x to the 6th from, well, what would be x to the 8th, x to the 10th, and so on, right? We've truncated it right here, yeah? So this is our approximation from our polynomial. And then this is how much we're off by, right? This would be our error caused by the truncation. Everybody agree with that? Right, because this series, if we went infinitely, would exactly represent 1 over 1 minus x squared. But since we didn't use the full thing, we only use these first 4 terms, we have some error. Right? If we were to plug in, let's say, a half into here, right? If we did 1 plus a half squared plus a half to the 4th plus a half to the 6th, we would know that the error would be a half to the 8th by a half to the 10th plus a half to the 12th, and so on. Everybody following?
Yes.
Okay, perfect. So let's just think just solely about this error. And because that's what we're trying to find out, is how much are we off by? Well, what does x to the 8th and x to the 10th and x to the 12th and x to the 14th and x to the 16th and so on, what do they have in common? Okay, yeah, next to the 2n. Okay, I see what you're saying there, Darius. Yeah, but starting at what point? At n equals 4, right? True? They've all got an x to the 8th in them, don't they? I mean, this has an x to the 8th in it. This has an x to the 8th in it, right? This has an x to the 8th in it. This has an x to the 8th. Each successive term has an x to the 8th in it, and then there's some stuff left over, right? So couldn't we take that x to the 8th and factor it out? And if I factored it out, what would we end up with? We'd end up with x to the 8th times, well, the first term would be 1, right? And the next term would be x squared, and the next term would be x to the 4th, and the next term would be x to the 6th, and the next term would be x to the 8th, and the next to the 10th, and x to the 12th, and so on. True? Do you all agree with that?
Yes.
What is this equal to? What is 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th plus x to the 10th plus x to the 12th equal? Exactly, Nick. It equals 1 over 1 minus x squared. So we'll note that the error that is caused by this truncation after 4 terms is x to the 8th. I guess I'll draw this over here perhaps. This is x to the 8th over 1 minus x squared, right? Or it's the next term after a truncation times the original series. True? What if we had a different geometric series? What if we had the series for 1 over 1 minus x cubed, what would that one look like? Should start at 1, and then be x to the 3rd, and then x to the 6th, and x to the 9th, and so on. Well, what if we truncated it at x to the 6th, let's say? Yeah. What would I end up with over here? I'd end up with x to the 9th times, well, this first term would be 1. And then the x to the 12th that I would have here would become an x to the 3rd, and the x to the 15th would become an x to the 6th, and so on, right? And so we see, again, that at the point where we truncated, our error was the next term times the original series. Good or no? And this will work for any geometric series. And remember, why is this gonna, it seems like that shouldn't make a lot of sense if you try to think about all real numbers, right? But what are these only valid for? These are only valid for -1 to 1. So if I take x to the 8th, that's a number that is less than 1. So what I'm multiplying by here is less than 1 times the original value. And so clearly that's going to be coming out to something that's smaller than what the original series itself actually equals. Okay. So that's the first error bound that we're going to talk about. And I'll put this on another page here. We call this the geometric series truncation error. And it's by far, well, maybe not by far, by a little bit, perhaps, the easiest truncation error that we deal with. It's the next term after the truncation times the original series. And if this was the AP test and they said, you know, what's the truncation error caused by truncating whatever at this exact point? And it's a geometric series, all you gotta do is this. Any questions on that? Everyone's good? Cool. All right, on to the second one, also an easy one, although we're going to spend a little bit more time investigating this one. No, Nick, it's not a method to make the series more accurate. It's a method that we use to determine, because we can't always just infinitely sum these series together. Sometimes we just need an approximation, and so we want to use a simpler polynomial to make the calculations quicker. So we truncate it at some certain value, and we use this truncation error idea to determine how accurate our approximation actually is. So we might say something like, okay, we want the error to be less than, 5/1000ths or something like that. So we say, where would we need to truncate this polynomial so that we know that we will always be within 5/1000ths of the exact value of it? Okay, because for some calculation, we might need to be within that range, right? We might need to make sure that the amount of some chemical element that is somehow represented through some series is within 5/1000ths. And so we know, okay, we can truncate it here. We don't have to do the whole series. Truncate here, we're within the range of this amount that we need, and we do our calculations. Does that make sense? Cool. All right. Perfect. Okay, so the next one here is called the alternating series error bound. And this one is also very, very easy. The important thing about this one is that guess what types of series it only works for? Only series that alternate, which means go from positive term to negative term, to positive term to negative term, to positive term to negative term. So if the series is an alternating series, we can look and see if the alternating series error bound will work. And so what the alternating series error bound says is, if our series has these three properties, which are the terms alternate in sign, that's does it alternate? Okay, easy. The second one is, do the terms decrease in absolute value? So basically, are the absolute values of each term getting smaller? So from 1 to a half to a third to a fourth, right? Forever. Right? And the terms approach 0 as their limit. So if I were to take, the limit as n approached infinity, right? Would that limit be 0 of this series, right? And so yes, this is going towards 0, right? 1, a half, a third, a fourth, a fifth, a sixth, a seventh. It's going to 1 over infinity, which is 0, right? So if those three criteria are met, right, the terms approach 0, they get smaller, their absolute value gets smaller, and they alternate, then the truncation error after however many terms, after n terms, is always going to be less than that next term's absolute value. So hopefully that makes sense, but suppose we were to truncate this right here at 1/3. Okay? If we said, let's approximate this series, or approximate the entire series by using 1 minus a half plus a third, we know that the value that we get is off by less than 1/4. It's off by less than the next term. Right? If I were to truncate this series at minus 1/10, the error we would get by doing 1 minus a half plus a third minus a fourth plus a fifth and so on down to minus 1/10, the error on that for the entire series would be less than 1/11. Does that make sense? Or no? We're not going to do a full proof of this, but we're going to at least investigate it with this series that we should know converges to the natural log of 2, because we proved that way back when. Everybody good so far? Ready to start seeing why this works? I hope. Okay. So first off, this series, why is this the natural log of 2? We should know this. I hope. In fact, I posted up some series that you should know. Maybe you saw that, maybe you didn't see that. Did you see that in Google Classroom, series to know? The natural log of 1 plus x is equal to the sum from n equals 1 to infinity of -1 to the n times x to the n, sorry, -1 to the n minus 1, x to the n over n. This is a series that we dealt with when we were talking about integration. Right, we integrated to get this series. Does that sound relatively familiar or no? I hope. Okay, good. All right, so all we're doing here is plugging in, plug in 1 for x. x. If I plug in 1 for x, I should get the natural log of 2 equals the sum from n equals 1 to infinity of -1 to the n plus 1 times 1 over n. True? If I plug in 1 for x on both sides of my equals sign here, I should get natural log of 2 equals -1 to the n plus 1, which just tells me that I'm alternating. And then 1 to the n is 1 over n, right? So this is just 1 over +1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5. Alternating terms, right? Good or no? Okay, great. All right, so let's first off make sure that does this series meet all 3 of these criteria? I think we already talked about that, right? The terms alternate in sign. They're getting smaller in absolute value, and it's going towards 0 as their limit, right? If I took the limit as n approaches infinity of this series, I would get 0, right? As n goes towards infinity, this is just 0 times -1 to the n plus 1, or 0. Okay. So if we were to look at the very first value of this series, suppose we truncated it right here at 1, right? We'd be over here. True? And we would then be able to say that the error, the amount we're off by, is less than 1/2. And the reason why is because here's 1/2. Hold on. What's the question, Molly? Why is it n plus 1, not n minus 1? No, it doesn't matter. N plus 1, it could be n plus 71. Just so long as this is an odd number. Right? All right, I mean, just so long as it's n plus some odd number there. Because the -1 to the n plus 1 or n minus 1 is just going to make it alternate. So first value I have to put in. Wouldn't it get off more than 1/2? I'm not sure what you're saying, Adrian. Molly, did I answer your question okay? Okay, Adrian, I'm not sure what you're asking. The value won't be under 1/2. True. Yeah, the value is not going to be. The value is not going to be under 1/2. No, it doesn't add a bigger number. It subtracts a number. It subtracts a half. All right. So here's what we need to do. So we haven't hardly started with this. So give me a second. Bear with me for a second, Adrian, to let me sort of get through a little bit of this, and then if what I'm saying isn't making sense, we'll go back and sort of rehash it. Okay. So first off, what is the natural log of 2? Because that's what this series is supposed to equal, right? The natural log of 2 is about 0.693 something, 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 something. So I'm just going to mark that in here. Natural log of 2, about 0.693 something, 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 something. Okay. So to start off with, we truncated at 1 and said we're at 1. Well, what is our error? Our error is whatever the difference between 1 and 0.693 is, right? 0.307 something, something, or probably 0.306 something, something, something. True? Everybody agree that that would be the error if I truncated at 1, about 0.3?
Yes.
Okay, perfect. So our next term, which was minus 1/2, right, is definitely more than 0.306. So we know that our error is always going to be less than this next term, which in this case it was 0.306 is less than that next term of a half. Now, suppose instead of truncating at 1, we decided to truncate it a half. Well, that means we need to do 1 minus a half, which is going to bring us back to here, right? So now we're here. Our next term is 1/3. Well, if I add 1/2 and 1/3, I ought to get 5/6, right? Which is going to be somewhere over here, right? When I add that next term in, the 1/2 that I'm at, plus the 1/3 is 5/6, I'm going to be somewhere over in this vicinity. Do y'all agree with that? The amount I was off between 1/2 and natural log of 2, this value is less than, it's not less than 5/6. It's less than that 1/3 that I had to go to get over to 5/6. Does that make sense? I hope. Well, suppose then we truncated it at this 5/6 value, 1 minus a half plus a third. Well, the error then will be less than this 1/4. And if I were to subtract 1/4 from 5/6, let's do this in a different color. That'd be 1/4. 5/6 minus 1/4 ought to be what? 7/12. So here I'm at 7/12, right? But this amount between 5/6 and the natural log of 2 is now less than 1/4. It's less than that next term, because every time that next term is going to bring me back onto the opposite side of the natural log of 2. I'm going to oscillate back and forth around this value. So every time the error between the actual value and where I'm at is less than that next term, because the next term will always flip me to the other side of the sum of that series of natural log of 2. Does that make sense? All right, cool. I'm glad that makes sense now, Adrian. Everybody feel okay about that? It's a little confusing to sort of like look at the picture, but the basic idea is every time I add a term in, I will go from, let's say if it's the beginning, I was at 0. I added the first term in. I went from the left of natural log of 2 to the right of natural log of 2. From the left of the actual sum to the right of the actual sum. Then when I added that minus a half, I went from the right of the actual sum to the left of the actual sum. Then when I added the 1/3, I went from the left of the actual sum to the right of the actual sum. And so every time the amount that I'm off is always going to be guaranteed to be less than the that next term, because that next term goes a little bit further than the error to get on the other side of the actual value. All right, so does that make sense or no? Everybody feel okay about that or not? Okay, just trying to make sure there's no questions. So that's all there is to the alternating series error bound. If it's an alternating series and if it meets these 3 criteria right here, then you are guaranteed that the error is always less than the absolute value of the next term after your truncation. So those are the first 2 types of error bound that we need to deal with. Everybody good? And you'll note that neither of those 2 necessarily had to deal with a Taylor series, right? This one was just a geometric series. This one is just any alternating series that meets these criteria. Right. So everything else that we're going to do today is centered around a Taylor series and the truncation specifically of a Taylor series into a Taylor polynomial. And this is where it's going to get a little bit more complicated. So when we take a Taylor series and we truncate it, we cut it off into a Taylor polynomial, it gives us two distinct pieces of that series. One of the distinct pieces is the polynomial itself, and then the other distinct piece is the remainder, which has a D in it. So I don't know why there's not a D there. The remainder, right? Which we call capital R sub n of x usually. Okay? So wherever we truncate, we are left with two pieces. We're left with the polynomial and we're left with the remainder. Right? And the remainder tells us how accurate that approximation is, right? Like we've been talking about. We truncate the polynomial after 6 terms. Well, the remainder is how much we're off by. That's how inaccurate our approximation is. It's the 7th term on, right? So what Taylor's theorem says, and it's a long proof of this that we're not going to go into. You can look it up online, I'm sure, and read about it, probably on like Wikipedia or something if you want. Maybe not Wikipedia, I don't know if the proof is there, but you could probably find it on Khan Academy or something. It's a fairly lengthy proof that's not actually that rigorous or difficult to follow. But the theorem says if that function has its derivatives of all different orders in this interval, you know, like it would have to do for us to write out a Taylor series for it, then we are guaranteed that our remainder is always less than or equal to the next derivative of the function evaluated at some value c, okay, where c is between a and x, so between whatever x is good for our interval, so whatever our interval happens to be for some series, right? It might be -1 to 1, some series it might be -infinity to infinity, depending on whatever the interval that this series converges for. Okay, so for some x on our interval, and between a, right, where a is the center of this radius, or the center of this interval of convergence, right? It's our value that gives us the radius of convergence. So it tells us that the remainder is always less than or equal to the next derivative of our function at some value c between x and a times x minus a to the n plus 1 over n plus 1 factorial. And this piece right here is just the same as each of these pieces, right? And this other piece with the n plus first derivative is essentially the same as this, except instead of evaluating it at a, we evaluated it at some value c. And the value c that we choose is the value on our interval that makes this entire thing, it makes all of this, it makes this whole thing, it makes the largest. Right, because normally we do this at the center of our approximation for all these other terms, right? That's why we have this a value, and here we do x minus 2 if that's where we're centering our polynomial. We do it x minus 5 if we're centering it at 5. We do it x plus 1 if we're centering it at -1. Well, now if our interval was between -5 and 5, let's say, then we would pick the c value between -5 and 5 that makes this whole piece here the largest it could possibly be. And we will say that the remainder itself is always less than or equal to the largest value that this term could obtain. And So we're not going to do the full proof of this because it would take us like the entire rest of the class period probably to set it up and get through it all. But that is the that is Taylor's theorem, and that is the largest possible value that this remainder could have is this. And it's the next derivative at whatever c value on your interval makes that derivative the largest over n plus 1 factorial times x minus a to the n plus 1. So what we're going to try to do with this is we're going to take a look at a couple of the series that we've already dealt with. The first one we're going to do, I believe, is sine x. So we're going to take a look at sine x, and we're going to use this error, this remainder form, to prove that it converges, the series that we found for sine x converges to sine x for all real numbers. And we looked at it, and it appeared that it did based on just inspection from Desmos, but that's just a sort of a hopeful guess. We can prove now that it is guaranteed to converge for all real x. And when we do this, this is called the Lagrange error bound. Right? It's the Lagrange error bound. It's the Lagrange form of the remainder. That's what this is. This is the Lagrange error bound. The n plus first derivative of c. I should probably write this. This is the that. This is the Lagrange, which I should write it so you guys can read it. Lagrange error bound. So what we have to do is we need to figure out what the largest possible value our remainder could be for this function or for this series, and then look at its limit as n approaches infinity. And if that remainder approaches 0 as n approaches infinity, then we would say that this should converge to sine x for all real x. If it doesn't, and there's just some set of values for which it will converge, then it will converge on that specific interval. But generally, what we use this Lagrange error bound for when we're doing this more theoretical stuff like this is to prove that it's going to converge for all real numbers. So we know that this is the function for sine x, right? So I'm going to sort of put that off to the side here. This is f of x equals sine x, if I write it out infinitely, which is what we've done. And let's write out the Lagrange form of the remainder if we truncate anywhere. So what does our remainder end up looking like? Well, we know that our remainder is less than or equal to the next derivative at some value c over n plus 1 factorial times x minus a to the n plus 1. And so what is the a value that we have here? Where is this series centered around? Is there an x minus something up here? Right, that's what our series looks like, right? It's x minus a, x minus a, x minus a. Well, what's the a value here? X minus 0, right? Yes, 0. So our remainder will always be less than or equal to this. So the x minus 0 can just become x to the n plus 1, obviously. But the thing that we have to focus on and worry about here is this. This is the next derivative of our function, evaluated at some value c on the interval that we're looking at. And our interval that we are hoping that this converges for is all real numbers. So what we have to do is think about what is the largest possible value of this. I guess I should write value. What is the largest possible, we'll make our question mark there bigger. What is our largest possible value of the n plus first derivative of sine x at some value c? Exactly, Ryan. It's 1, right? We know that the derivatives of sine are always positive or negative sine x or positive or negative cosine x. Right? The derivatives are always positive or negative sine or positive or negative cosine. And so no matter what value of c I plug in, the largest possible value that this could occur at is 1. The smallest it could possibly occur at is negative 1, right? This derivative of sine x at any value c is always between negative 1 and 1. So which value of these between negative 1 and 1 will make this piece the largest? One, right? So we end up with x to the n plus 1 over n plus 1 factorial as the bound on our remainder. Our remainder, wherever we truncate, is guaranteed to at most be x to the n plus 1 over n plus 1 factorial. Right? And so the next question then is, what is the limit as n approaches infinity of x to the n plus 1 over n plus 1 factorial? If that limit is 0, then this will converge for all real values of x. But if it is only 0 for certain values of x, then that means that it only converges for those certain values of x. So what is this limit? Is it always 0 for all values of x? Yeah, it should be, right? We should be able, and we haven't really dealt with factorial, but we should be able to say that factorial growth is faster than this numerator, which is exponential growth, right? Isn't the numerator is exponential, right? Because x is just some number between negative infinity and infinity, some concrete, some real number value. We're raising it to the power of a variable n plus 1, right? And the factorial growth as we go towards infinity will be faster than the exponential growth. And if you think about it, sometimes that's a little hard to conceptualize, especially because you've always been told that exponential growth is the fastest type of growth that there is. Well, that's a lie. It's not. Factorial growth is faster than it. Because what is factorial growth doing? It's multiplying the same number of times as this thing is, but this is multiplying some number. Suppose that number is 1,000,000. We're doing 1,000,000 to the, whatever n is plus 1. So 1,000,000 times itself, let's say 1,000,001 times. Well, this would be 1,000,001 times 1,000,000 going down. This is smaller. But if we go to 1,000,000 to the 1,000,001, and this is 1,000,001 factorial, this number is already going to be substantially bigger probably than this one is. And as we go towards infinity, this factorial will always be getting bigger much, much, much more quickly than the exponential growth. This equals 0, and we would say that it equals 0 for all x. So we would say this converges for all x. We might only at this moment be able to say that it converges for all real values of x. But interestingly enough, as we will find out later today, hopefully, if we get there, this actually converges for all complex values of x as well, which is actually really cool and will prove us something really neat, hopefully by the end of the class today. So good or no? Any questions on that? I know that's a little out there perhaps, but. All right. So this is our remainder form. Just I'm going to put it out here once more. We think about x minus a to the n plus 1. This gets bigger always exponentially as n increases. If the value of this x minus a is bigger than 1, but it gets smaller if the value of that absolute value of x minus a is less than 1. The n plus 1 factorial gets bigger no matter what, right? And important to point that factorial growth is more rapid as we go towards infinity than exponential growth. And then this is the thing that sort of throws a wrench into it often, is that the behavior of this depends not only just on the function, but also the value of c that we choose. And so we can use this whole remainder bounding thing, like I said, to prove, like we just did with sine x, that it converges for all real x, for cosine x, that it converges for all real x. It can be used for e to the x. We're going to use it for a case of e to the x. We're going to use it for e to the 7x or something like that, I think is the one I have in here in a minute to prove that that converges for all real x. But what we need to confirm as we go through is that for what x values does this whole thing have a limit as n goes towards infinity of 0. And if it is for all real x, then it converges for all real x. If it's only for x between -1 and 1, well, then that's what it converges for. So the remainder bounding theorem says, and this is all the exact same thing essentially that I had before, that my remainder, if it is less than or equal to some constant m and some constant r, if I can find these values for m and r such that my remainder is always less than or equal to this thing, it means that it converges for all real x. Right, so as long as I can find a bound on, an upper bound on my remainder by plugging in constants of m and r, I should be able to conclude that my series converges for all real x. So what this is saying is, as long as this piece of my remainder, right, because my remainder is effectively this, it's effectively the same thing, except that I've replaced the derivative piece with m times r to the n plus 1. Right? Well, this r to the n plus 1 is adding more exponential growth. So as long as this piece does not add more factorial growth, something that is going to cancel out with this factorial growth, then I'm guaranteed that my series converges for all real x. So what we're going to try to do, and you don't need to necessarily write all that down right this second. If you want to go back to it, you can. in the notes. But what we're going to do is we're going to try to prove that the Maclaurin series for e to the 7x will converge for all x. That's going to be our goal. And so we need to first think about our derivatives. And we need to make the derivative piece of it less than or equal to some m times some r to the n plus 1. Because I can be already guaranteed that the x minus a to the n plus 1 over n plus 1 factorial that shows up in both of these will approach 0. So if I can make this inequality true by picking some constants of m and r, I can be guaranteed that this function will converge for all x. And so what do the derivatives of e to the 7x look like? The first derivative is what?
7e to the power of 7x.
Okay, and the second derivative is? And the third derivative is? What's the second derivative? Yeah, 49 e to the 7x. And the third derivative? Well, let's see. This is 7 squared e to the 7x, right? And this is 7 cubed e to the 7x, isn't it? So what's the n plus first derivative? Evaluated at c. Should be 7 to the n plus 1 times e to the 7c. Do y'all agree with that?
Yes.
So the question then is, are there positive constants of m and r so that I can make this statement true? And the answer should be yes. Right? If r equals 7 and m equals e to the 7c, doesn't really matter what that c value is. And if I just let m equal e to the 7c, what do I have? I have 7 to the n plus 1 e to the 7c is less than or equal to 7. Sorry, e to the 7c, 7 to the n plus 1. And that's always true. This is true for any value of c from negative infinity to infinity. And since that's true for all c values from negative infinity to infinity, that means that e to the 7x converges for all x. It means that this chunk here is not contributing anything more than exponential growth times some constant. And as long as this derivative piece from our remainder is not contributing any more rapid growth than exponential times a constant, then this thing must converge for all real numbers. Good or no? This is like the theoretical stuff that you're probably not going to see on the AP test. But what we will see on the AP test is using this idea to bound the error from a truncation, which is what we're going to do with these next couple of problems. So we're going to do this one in two different ways. We're going to use the alternating series test, or the alternating series error bound. And we're going to use the Lagrange error formula to find a bound on the error for the first two terms of the Maclaurin series for natural log of 1 plus x, and we're going to use it to approximate that we've used to approximate f of 0.1. So what should we do first? Probably write out the series itself, or write out the first few terms of the series, because we're going to truncate after 2 terms. So what does our series look like? for natural log of 1 plus x. First term should be first term should be x. Right, remember we had it written down earlier. Right, it's the sum from n equals 1 to infinity, -1 to the n plus 1 or n minus 1, depending on how you feel about it. X to the n over n factorial. Sorry, not n factorial, just over n. So the first term should be x. Right, if you plug in 1, that's x to the first over 1 times 1. And then the next term should be minus x squared over 2. And then our third term should be what? X cubed over 3. Everybody agree with that? And so on. But what are we doing? We're truncating it right here after just 2 terms. So the alternating series error bound says that if we were to approximate the natural log of 1.1, right, plugging in 0.1 for x, that the amount we're off by is just the absolute value of that next term. And what's that next term? It's using the alternating series error bound, it should just be 0.1 to the third over 3, which is what? 0.0003 repeating, I believe. Does that make sense to everyone? That's the alternating series error bound, right? That's a pretty easy one. If you know the series, right out the series, we know that we already showed earlier that this one alternates, that the terms are decreasing in absolute value, and that the limit as we go towards infinity is 0. So just take the next term, evaluate it at 0.1, and that's how much we might be off by. We would know we are off by less than this amount. Good or no? Okay. What if we wanted to do it using the Lagrange error bound? We know that the error should be off by the third derivative at some value c, right? Because we're truncating after 2 terms, so the next term would be the third term. So the third derivative at c times x to the n plus 1 over n plus 1 factorial. And so what is the third derivative of the natural log of 1 plus x? Well, the first derivative is 1 over 1 plus x. Right? Second derivative is what? Should be -1 over 1 plus x squared. And what's the third derivative going to be? Should be +2 over 1 plus x cubed. Okay. So that's what we should have here. We should have 2 over 1 plus c to the third times our x value. What's our x value here? Still 0.1, right? Yep. N plus 1 is 3, right? Because we're on our third term here, third derivative, third term. over n plus 1, 3 factorial. And so now we need to choose a C on, well, what is the interval of convergence for this series? It's -1 to 1, right? We need to choose a C on -1 to 1 that makes this the largest it could possibly be. Makes this whole term the largest it could be. So what value between -1 and 1 makes this whole term the largest it could be? C equals remembering that this is in the denominator, so the larger the number in the denominator, the smaller this thing becomes. So we want this number in the denominator to be the smallest it could possibly be. So what value between -1 and 1 makes this the smallest denominator or the largest value? Exactly, C. We choose C equals 0, which then gives us 2 over 1 cubed times 0.1 cubed over 6 as our error bound. And if we were to go back through and do all of this again, we'd have 0.1 cubed, which is 0.001 over 3, which is 0.0003 repeating once again. And so we'd find that the bound on this error is, once again, 0.0003 repeating using the Lagrange error bound. We know that the error will always be less than that. Good or no? All right, one more of these, and then we're going to do something cool here at the end. So we've got a second order Taylor polynomial for our function, some function f of x. We're not given f of x, doesn't matter. Around x equals 2, and we're using that as an approximation for our function. And we are given the information that, oh, there should be another absolute value sign there. The absolute value of the third derivative of f of x is always less than 2.3 for all x between 2 and 2.5. So that's giving us a bound on what the third derivative of f is, which is going to be helpful to us. We want to show that, should have another absolute value, I don't know what happened to my absolute values there, that the actual value of our function, okay, so the full series, minus the second degree Taylor polynomial. So what's the full series minus the second degree Taylor polynomial? What is this whole thing? What is that telling us? This is our series minus the polynomial gives us, use the series minus the Taylor polynomial that we truncated from the series gives us what? Here's my full series. Here's my truncation. What does that give me if I take my full series and I truncate something off? It gives me my error, or as we've also been calling it, my remainder. So this is our error, or it's our remainder. The full series, the function itself, minus the Taylor polynomial, the second order Taylor polynomial approximation of it, gives us the error. So we want our error to be less than 0.05. That's what this question is asking us. How do we make the error less than 0.05? Well, that's what we need to show. We need to show that the absolute value of all this, we don't need to show all of that absolute value. We got x minus 2 to the n plus 1, right? Because we're centered at 2 over n plus 1 factorial times the n plus first or third derivative at c. Okay. We want this to be less than 0.05. That's what this question is asking. Is can we show that this is true? And so we need to take the values of c and the value on our interval of x that will make this thing the largest and show that it's less than 0.05. So what value of the third derivative of f is the largest possible value that it could be? The largest thing, it's not pi. The largest thing that the third derivative of f at c could be is what? It's written in the problem. What is the largest possible value that our third derivative could take on? 2. Yeah, I mean, we'll just use 2.3, even though it says it's always less than 2.3. So we've got 2.3. What's the largest possible value that x minus 2 to the n plus 1 could take on? Between 2 and 2.5. Plugging in, let's say if I plug in 2, this is just 0 to the third power, right? If I plug in 2.1, it's 0.1 to the third power. If I plug in 2.5, it's 0.5 to the third power. Which of those numbers is going to be the biggest? Plugging in 2 to make it 0, plugging in the largest, 2.5 to make it 1/2 to the power, or plugging in something in between to make this a smaller decimal raised to a power. Putting in the largest possible x value, we'll do that 2.5 minus 2 over 3 factorial. And what does this equal? This is 2.3 times 1/2 cubed which would put us with a, I'll just do this down here, right? 1/2 cubed is 2 cubed down here. And then our 3 factorial is 6. And what is 2.3 over 48? Is it exactly 0.048? Well, 0.048 is less than 0.05, right? And so we said the largest possible, put in the largest possible values to our remainder. We got 0.048, which means that the error must be less than 0.048. And if it's less than 0.048, well, then it must be less than 0.05 also. Good or no? We're going to practice a lot more of these, especially as we go into our free response series questions. All right, let's do one more cool thing. So this right here is not the cool thing we're going to do. This thing right here is the list of all the series that you need to know. It's up in Google Drive also, but it'll be saved up with the notes today, so make sure you know those. Now, what I'd like to do, real quick, we got like 5 minutes, and I think that's enough time to do it. And if we have to go over a minute or two, well, I might go on, but you'll think that this is really cool because it's something we've sort of talked about sometime probably, but we can now prove it. So we got e to the x equals the sum from n equals 0 to infinity of x to the n over n factorial. That's a series that we know to be true, right? Yep, for all real numbers x. Well, we're going to take a leap of faith here, and I'm going to tell you that this is not only true, just like I said for the sine and the cosine one, is not only true for all real values of x, this is true for all complex values of x as well. And so if I were to write out the series then for e to the I times x, what would that look like? It should look like I times x to the n over n factorial, right? That's just how we do these series, right? We can just take any argument of this e to the power and put it into our series. And what does that series become? At n equals 0, it should just be 1 still. But so this second term should then become I times x. And the third term, well, is going to give us an I squared, right? When we plug in n equals 2. And I squared is negative 1. So we're going to have a negative x squared over 2 factorial. And then we're going to get a plus, and we're going to put this, sorry, we don't get a plus, we get a minus I cubed. We get a plus I cubed, which is minus I, right? I cubed is negative I, x to the third over 3 factorial. And then we're going to go right back to a positive x to the fourth over 4 factorial. And what's the next one going to be? It's going to be a positive, and then it's going to be I to the fifth. I to the fifth is just I, x to the fifth over 5 factorial, and so on. And so we would probably see that a pattern would develop here, that we're going to get, first off, terms that go from 1 to negative x squared, if I skip the I, to positive x to the fourth, to a negative x to the sixth. And then we're going to have an I x and a negative I x to the third, and then a positive I x to the fifth, and then a negative I x to the seventh. And so what I'm going to do is I'm going to write these out separately, one with just the non-complex numbers, one with just our real numbers in it, and one with the complex numbers. So we got 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and so on. And I'm going to add to that I x minus I x cubed plus I x to the fifth. Well, what do they all have in common? They all have an I in common, don't they? So I'm going to factor that I out. I times x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus x to the ninth over 9 factorial, and so on. Everybody agree with that? I promise there's a really cool payoff here. What is this? This is a sum from n equals 0 to infinity of alternating, so negative 1 to the n, and looks like that's x to the 2n over 2n factorial. That should look familiar, I hope. Plus, what's going on over here? We have I and a sum from n equals 0 to infinity of, well, what is this one? It's alternating, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. That should look familiar too. Both of those look a little bit familiar to you?
Yes.
Yeah. What is the first one?
Cosine x.
And what is the second one?
Sine of x.
And what did we start with? We started with e to the ix. So e to the ix should equal cosine x plus I sine x, which is pretty cool because, oh, I didn't mean to cross that out, which means we're we can, using complex values, relate e, our exponential constant, to both of our regular old trig functions using the imaginary unit. And this is true for all real x. And the even cooler thing about this is that if we evaluate this thing at x equals pi, we end up with e to the I pi, which you've probably seen before, equals the cosine of pi plus I times the sine of pi. And that tells us that e to the I pi equals cosine of pi, which is 1. And I times the sine of pi, well, the sine of pi is 0. I times 0 is 0, which gives us the very famous Euler's identity, cosine of pi is a negative 1, e to the I pi plus 1 equals 0, right? Which is, you've seen me and heard me talk about this probably at some point. This is Euler's identity. And it comes directly from expanding out e to the ix, dividing it up into the sine and the cosine series, and evaluating it at pi. Isn't that amazing? Aren't you all amazed? Okay, I guess not.